Thank you very much. When Farah approached me a number of months ago about this event, it didn't take me very long to decide what it was I was going to talk about. Structural optimization and efficiency has been a prime interest of mine through my career here at Arup and has played a major role in a lot of the work that I've done over the past 12 years. What was a bit of a challenge was to work out how I'd talk about it for 25 minutes. So what we've decided to do is I'm going to talk about some of the history and how structural engineering efficiency has informed some of the master's work. I'm going to talk about some of my own work and how that's been prominent in that. And then finally have some thoughts on how it might inform the future and how structural engineering might change in the coming years. It's customary, I think, a requirement to quote Vitruvius at these talks and his requirements of firmitas, utilitas, venutas, that it be solid, useful, and beautiful. Doesn't quickly identify him as being someone who's driven by efficiency. However, his works do give us the best understanding that we have about structures from the period, such as the Pont de Gard, and through the change in the module of the arches and the increasing scale of elements, I kind of feel that structural efficiency did play a part in developing these structures. It's difficult to really separate stone architecture and timber architecture from the engineering of these early periods. And it's not until the Industrial Revolution and the mass production of iron that we start to see the emergence of the modern engineer. One such engineer, and the godfather of engineering, is Thomas Telford, who was the first president of the Institute of Civil Engineers, and who was working in a period where steel prices, or iron prices, were incredibly high. He was actually designing further back here, where the cost normalized against current prices was about 20 times what it is today. This focus drove his theory that efficiency in material, economy of construction, and the appearance of the final form should drive the design of structures such as the Menai Straits Bridge, shown here connecting Holyhead to the British mainland. It was built in 1826 and was such a leap forward in construction. Suspension bridges hadn't really been used outside of South America. This was the first real example of it. And it was also massively reduced the weight of structures when compared to other solutions that might have been adopted, such as masonry arch spans. And I think this sudden leap forward unearthed a whole load of other structural issues and responses that hadn't been considered, and the bridge galloped under a particularly severe Welsh storm, and there was massive damage in 1836 to the deck. That damage, had the lessons been learnt from it, might have reduced some of the issues that were later experienced 100 years later at the Tacoma Narrows disaster, where Galloping Gertie galloped too far and collapsed into the water below. Whilst Telford used simple structural diagrams and one-to-one testing to develop his structural designs and theories, Gustav Eiffel embraced modern mathematics and used that to completely rethink and optimize the design of iron lattice structures, in particular the Crescent Bridge in TORRE, and of course his tower located in the center of Paris. From reading about him, you get the feeling that he was incredibly focused on structural efficiency, and stated that the first principle of architectural beauty is that the essential lines of construction be determined by the perfect appropriateness to its use. In the case of the tower, he was stating that its use was to resist wind, and that subsequently, I submit that the curves of its four piers are produced by our calculations, rising from an enormous base and narrowing towards the top, will give a great impression of strength and beauty. You might get the impression that he was dogmatic and uncompromising in this opinion. He wasn't, and towards the latter stages of the design, he was forced to introduce arches at the base because engineers rooted in masonry construction couldn't believe that such a structure could stand up without arches. You might also think that it was loved. It wasn't. A number of prominent artists of the time completely dismissed the design, and one of them stated that the best place to eat in Paris was the Eiffel Tower because he couldn't see the Eiffel Tower. Whilst Eiffel was forced to compromise and adjust his designs for political reason, the designer and bridge designer Robert Maillard seemed to have an awful lot more freedom in his work in Switzerland. His early work, such as this bridge at Zeus, has some architecture and engineering merit, but he knew that if he was to scale it up, the concrete located within the webs would be of such a scale that it would become uneconomic and untenable. Over the course of a number of bridges over his career, he developed the idea of removing all of that material and finally arrived at this stiffened deck that would work to stabilize an incredibly thin arch that would prop off some very thin pillars. He also developed a whole new way of designing these bridges that was completely dismissed by the academic elite at the time, but has subsequently been proven to be accurate. There's numerous examples where structural efficiency has driven the design. Gaudi's work using hanging models that directly inform the shape of projects such as Sagrada Familia. Nervi's work looking at the flow of principal stresses and the subsequent results on the soffits such as this. And then Fazlur Khan and the way that he took the structure out onto the perimeter and resulted in projects such as the Hancock Tower, which happens to be my favourite project. And I was lucky enough to spend 3 or 4 months living near its base. The academic from Princeton University, David Billington, took this idea a little further in his book, The Tower and the Bridge, where he coined the idea of the structural artist and stated that their principles be efficiency, economy, and elegance. He also stated that it was false that beautiful structure demanded the assistance of non-engineering consultants on aesthetics, i.e. architects. Whilst I have some sympathy for his thoughts, I still believe that the best structures come out of close collaborations between different design disciplines. So that was a brief canter through history and gave me some insight into how structural efficiency has driven the work of the past masters. And now I'm going to talk about some of my work and how efficiency has informed that. As a junior engineer, you join and you start doing an awful lot of beam and column calcs, and it's all essential stuff, but it does get a little bit tedious after the first few thousand. And for that reason, I've always started to look at IT and how that might be able to streamline that process. And of a particular scenario was the GUANGZHOU Financial Center, which is a high-rise building located in China. I was responsible for the design of the diagrid and spent an awful lot of time optimizing these elements and wrote a script that would vary the spacing of the diagrid around the perimeter. The final design that we arrived at pushed out the diagrid in the middle, condensed it around the corners, and in so doing stiffened the building and allowed us to reduce the steel tonnage by about 8%, which over such a large-scale project is a significant amount of steel. Fast forward 7 years and I'm still writing computer scripts to optimize steelwork. The project is Singapore Sports Hub, which is the longest span dome in the world, 305-metre span, and it encloses a new national stadium for Singapore and supports a movable roof that opens and closes in order to expose the pitch below. When considering these projects, you get an awful lot of challenge from your contractors and clients about the efficiency, and you generally talk of efficiency as the kilograms per metre squared required to achieve the span. This graph shows the kilograms per metre squared for numerous projects at both Arup and other consultants. And the typical rule of thumb is that for every metre of span, you require an additional 1 kilogram per square metre of steel. You can see, therefore, that the 300-metre span of Singapore Sports Hub would theoretically require 300 kilograms per square metre, and we were able to deliver it for closer to 120 kilograms per square metre. There's numerous reasons as to why this is. The form of the stand follows the structural pattern and provides a shell structure which is efficient. We undertook extensive analysis of the wind tunnel testing and took advantage of the aerodynamic shape of the dome. And also there's a kilometre-long post-tension ring beam that provides a very stiff support for it, which is fundamental to get efficiency out of projects such as this. However, one of the key reasons we were able to provide the tonnage we did was due to the software that we wrote that took all unnecessary material out. The vast majority of material in these roofs is primarily there to hold itself up, especially in benign environments such as Singapore, where wind and seismic forces are low. The software allowed us to optimize the design, consequently reduce the steel, which would allow us to reduce the loads, which would allow us to then further optimize the structure. And this positive feedback loop, along with cloud computing to deal with all of the wind loading allowed us to take all the necessary material out of the structure. This is an image of it looking back towards two other Arup projects, the Flyer and Marina Bay Sands. A year ago, I inherited the design of a high-rise tower in Mexico called TORRE REFORMA 509. The tower, shown here in the foreground, is located on REFORMA, which is the main boulevard in the central business district of Mexico City. Mexico City is a particularly interesting place to work and design because it's built on an old lake. And the actual area of Mexico City isn't that seismic, but the areas where you're building on the lake gets excited by earthquakes located along the Pacific Rim and causes significant damage in the case of the 1985 earthquake in Mexico City. In seismic buildings, you need enough strength to carry the forces induced by frequent earthquakes, but at a more extreme event, you need a predictable way of absorbing the energy and resisting collapse. We found that by adjusting the software that we had written for Singapore Sports Hub, we were able to reduce and remove all of the unnecessary strength out of the building, primarily located within the bracing structure along the perimeter. That by doing that, we were reducing the forces imposed onto the building, which would allow us to further reduce the size of those elements. When compared to the benchmark design, we saved nearly 1,000 tons of steel, which in terms of local cost was about $3.5 million. So that's a brief look at some of the work that I've done, and now to look at how the future may change and how structural efficiency may inform it in the going forward. I like this quote from William Gibson, that the future is always here and it's just not evenly distributed. And I think that's particularly apt to our industry. If you go back to the 1960s, the advent of 3D software was developed for the aeronautical industry. By the 80s, they were using this for designing complex structures and doing multidisciplinary coordination for projects such as the Boeing 747. But yet, we've only really been adopting that in the last 10 years within the built environment and our work on BIM modelling. I'm always interested in looking at both aeronautical and automotive because there's always that drive and that efficiency on the efficiency of materials, and so it kind of hits a chord with me. In terms of the automotive, I've been interested through this talk to look at how they use different materials. So a typical chassis in a car may use 5 or 6 different grades of steel. In terms of the whole car, you might have 100 grades of different steel. With the higher strength elements, just those areas where they're not expected to absorb much energy, and the lower strength, high ductility steels are located in areas required for energy absorption in the event of a crash. Not only do they optimize the distribution of different grades of steel, they also open themselves up to a vast range of different grades. So this has strength and elongation on the y-axis, and these are all the grades that the automotive industry tend to use and are focused on. This is what the construction industry uses, which I think is a bit of a missed opportunity. And there are examples, specifically in Japan, where they're using 1,000 MPa steels, but they're also using fire-resistant steels that don't require intumescent paint. But there doesn't seem to be that pull or push within our market in order to bring those to fruition. The other interesting thing was to look at how production has changed, specifically in the aeronautical industry, where now about 25% of their componentry is made through 3D printing. This is a typical bracket taken from an Airbus. And there does seem to be a trend of this gaining a little bit of traction, but very slowly within the construction industry. This is a proposal in Amsterdam for a 3D printed house, which is apparently going to happen. But I have done, through a bit of research, found that in China they've already built a 5-story house, and they did so in 24 hours using a 3D printer. So this technology, if that is true, has some significant benefits. Finally, been interested over the last few years looking at how the design processes that seem to be adopted in these industries. So a car bonnet may be prescribed or at least informed by some very complicated genetic algorithms that optimize the amount of material until everything there is required purely for structure. We've done a similar study. This is a typical node that's located, work we've done with Delft University, This is designed in a conventional manner and fabricated in a conventional manner. This uses some complex genetic algorithms to derive its shape and then a 3D printer to deliver it. I don't think we'll be doing those imminently, but this logic may start to come to fruition over the coming years. So as a little summary of how I see the future panning out, I think we've still got some way to go with higher performance materials. Concrete has come on leaps and bounds, but steel, 10 years ago we were using S355, we still are. I think we'll see that improving, hopefully. If 3D printing really can work at a building scale, and it is shown to have the program and cost advantages, then it may change the focus on material efficiency. It may make us more interested in optimizing our materials, and that might drive us towards some of the strange optimized forms that I showed at the end. Finally, I firmly believe that structural efficiency leads to better engineering and better buildings. Thank you very much. I think questions.
Your work that you did at Singapore and in Mexico in getting to those incredibly low tonnages of steel, how much of that was dependent upon you being able to change the geometry of the building to best fit the structural form?
So in the terms of the project in Mexico, the 950 tons essentially uses the same structural system between the two. And all we've done is to optimize the elements within that configuration. The efficiency from Singapore Sports Sub, some of it comes purely from the form of it and the fact that we've got a very stiff base. But I think also, and we haven't quantified it, but also a lot of it comes from the work we did with the optimization software.
CLT, it's been around for a long time, but people don't tend to use it, I suppose, more than, say, schools. And low-rise buildings. If you speak to some of the big players like KLH or Urban, they'll say they can go up to 13 stories. Do you see that as, obviously we can get more efficient in steel and concrete, but do you see CLT as another way of creating a building that can be put up quickly and with very low carbon footprint in the future?
Yes, and I think there's an example in South London where that's been done. But at the moment, it does really constrain you in terms of span. So I think probably confining yourself to residential developments at the moment purely from span reasons. But yeah, why not?
You've talked a lot about efficiency in terms of reducing the volume of material that you use and therefore the cost of buildings. How often are you asked to reduce the energy, embodied energy of structures?
I've always felt that one goes with the other. Clearly, if I'm reducing the amount of material, purely structural material, then I'm reducing the amount of embodied energy within the part of the building that I have control over. Through the design development, if someone's telling me that actually what you need to do is you need to do something more expensive materially in order for us to provide benefits in terms of environmental design, then that kind of comes through that discussion and we play that off against each other, and generally the architect decides who wins.
I thought the talk was great, actually. The sort of historical component about the role of structural engineering in great architecture, and I think it's clear that Arup has a good sort of grasp on the importance of structural efficiency in great architecture. A lot of the content, being a lecturer, we teach classes on history, we include architecture, structures, and I'm taking some notes from this guy.
What I really appreciate about Arup is the awareness of history and the sense of history, and Ove's portrait here on the wall, and then the way the talk incorporated kind of the history of engineering, but how that leads to the excellent work that's being done here today. It's really a tremendous opportunity for our students to be here at Breakfast with Arup. We brought about 18 students from the States, and they learn more in an hour with Arup than they would learn in a whole term back back at home, because we're just getting them exposed to this really cutting edge advanced design it's not in the magazines yet, and seeing projects like the Singapore Stadium, just tremendous opportunity for these students.
I really enjoyed it this morning. I enjoy always coming to these talks in the morning, because it sets you up for the day, sets you on a different tangent to, with your own projects, to think about how things might be different. But I very much enjoyed the history, the sort of the background, and then to see Will then describing how some of his work's been informed by the masters, and just ideas for the future, really.
The whole idea of optimization, I mean, as architects, we're always interested in that. A lot of the discussions tend to be about how we can reduce structure, so it's really speaking our language, I could say. But yeah, optimization, obviously, we've got, with the scripting and the modern tools that we've got, we can go a lot further with it than we ever have. And nature's been doing it forever, so I think we're on the right track. I think the question is not a question of will and do we want to do that. It's a question of how to integrate that into the process so that it's effective, so that we can optimize, so that it feeds into the design process, so that we get something which is elegant, which is light, which is optimized in every way.
I thought it was very interesting. I'm still pretty new to all this as far as materials go. I'll be taking a steel class next semester, so it was really cool to know how steel is moving and where it's going to be in the future, hopefully the near future, and just how it's being used in all the new projects and innovative projects.
I thought it was really influential, actually, because sustainability is a huge impact in all of our curriculum. So it's great to see it actually in the field. I'm going into my senior year, and for our design, we have to create our own high-rise. So I can see myself actually further developing the sustainability and materials that was presented today. I feel like sustainability and efficiency go hand in hand, because we're only on this planet once, and to be efficient, you need to be sustainable.
Well, the reason that I come to the Arup breakfast seminars, kindly invited by you and your team, for the last couple of years, is a part of my role at the Finnish Embassy's Trade Commission is to identify where there is demand in the UK for a particular product or service that is innovative, and then match that demand to supply in Finland. And one key area where we've identified there is a particular market for Finnish expertise is the built environment. And I've learned much of that, Arup, by coming to these seminars for the last 2 years and being a friend of Arup. I got to know Arup about 10 years ago because one of the companies that I represent is Tekla. And Tekla do the 3D visualization you use for your buildings. And we invite Arup to the embassy for discussion forums with the ambassador. So as a consequence, I've learned quite a bit about what's going on in the UK in relation to the built environment. And I'm organising a seminar in Helsinki in September devoted to green build, with a focus on sustainability in the built environment. And key areas will be eco-design, waste management, sustainable building materials. And we're putting that together based on the inspiration, actually, that I found coming to these breakfast seminars. And that's sponsored by the Finnish Ministry of Foreign Affairs. So that's the plan.